Hello, everyone, and welcome to this symposium about multi-echo fMRI methods and application. I'm Stefano Moya, and in the upcoming 5 minutes, I'm going to introduce you or refresh your knowledge about multi-echo. When we think about our standard fMRI acquisition, we normally have a repetition time, ATR, that starts with a pulse, an excitation pulse. After which, after the echo time, we sample the space. If we do it at once, we get a 3D volume. And if we do it multiple times, once per TR, we get a time series for each one of our voxels. Now, this echo time is set so that the sampling happens at the peak of the signal decay. And that is important because we're basically getting the best signal we can get. The problem is that different areas of the brain have different signal decays. In areas with dropout, the peak of the signal will happen earlier. In other areas, it will happen later. And this is where multi-echo will come in help. Because if we can collect different volumes, we can sample the space at different echo times for each TR. And if we do so, we end up with multiple time series for each voxel. And the first thing that we can do with them is basically optimally combining them, which is a step that can be as easy as doing a weighted sum based on the contribution of each volume to the signal decay. In this way, not only we can retrieve the signal from areas that will normally not have it due to the dropout, but we can also improve our spatial contrast to noise ratio and our temporal signal to noise ratio. Not only, if we assume that the brain is a single compartment, and we assume that the signal has a mono-exponential decay, we can express the signal in percentage change as the difference between two terms, plus some statistical noise. And the nice thing is that one of those terms is linearly dependent on the echo time, and it describes magnetic changes related to the bold signal, while the other one is non-dependent to the echo time, and it represents the magnetic changes non-related to the bold signal, and normally attributed to either noise, like motion, or artifacts. This model is incredibly helpful because, for instance, if we acquire just two echo time, in which the first one is very short, towards zero, we are basically collecting the non-bold related signal. And we can remove it from a later signal acquired with a longer TR. Beg your pardon. Otherwise, we can have our optimally combined signal and apply independent component analysis. And then we can fit each of the independent component time series to either models, either terms, in order to classify them either as good signal or noise. Today, our four speakers will tell us more about multi-echo in general, and we will start with Dan, that will tell us how multi-echo can be a choice that we can consider when we want to plan an fMRI acquisition. Then Elizabeth will introduce us to the Tedana community and the Tedana software, a denoising approach based on independent component analysis I was explaining earlier. Then Cesar will talk about multi-echo in data processing, and especially how we can use multi-echo to improve the deconvolution of the signal and improve the estimation of neural-related signal. Finally, Angie will explain us what it is to do multi-echo fMRI in practice, and especially what are the steps we have to go through if we want to set up a multi-echo fMRI study for the first time. Before leaving the stage to our speakers, I would like to invite you to ask questions in the chat. We will be there to answer to them. Probably we will be incredibly sleepy due to the time this symposium will go live, but we will be there to answer. And otherwise, you can write us an email, either to me or to the speakers, or have a look at the Tedana documentation, where you can find more information about multi-echo and more material to read. You can also get in touch with the Tedana community on Gitter, or read some papers about the topic. You can find a list here. Thank you very much and have a nice symposium.
Thank you for joining us today for our session on multi-echo fMRI methods and applications. For my talk, I'll focus on how to decide if multi-echo fMRI can improve your study. I'm dividing this talk into 3 general sections. The first is I want to frame multi-echo fMRI as one of many acquisition choices as opposed to sort of a binary decision, yes or no. I'm going to give one example how a multi-fMRI can help with your studies. And I want to conclude by talking a little bit more about how to evaluate whether you should use multi-echo fMRI with open eyes. So I'll start by the most common question I've heard recently, which is, well, I want, multi-echo fMRI sounds interesting, but then I can't get a short TR because there's obviously a lot of people interested in short TR studies nowadays. I'd rather frame that question as how many echoes do you want for how short a TR? And just because many people here might not know all about multi-echo fMRI already, I want to just take a little step back and make sure everyone's on the same page. When we talk about single echo fMRI, you have an excitation pulse in black. Then there's some unused time that waits that you're collecting data when the T2 star signal is at its peak. And then there's this readout period in green. And the distance from that excitation pulse to the middle of the readout period is called your echo time. So this is a typical example of a single echo fMRI acquisition. And the distance between those peaks is the TR. If I want to be pedantic, you can have multiple you generally have multiple excitations per TR, either for, to collect a full volume, but the general concept holds. For 3 echo fMRI, instead of having that unused time, you start collecting the first echo immediately, followed by a second echo, and in this case, the third echo. And what you could notice is that if you look at the right side with the TRs, the top dashed line is the TR duration for single echo, and the lower one is the TR for 3 echo. And you can see it does take more time, but it's a little bit more than a third more time. So it's not 3 times as much. It's just a slightly more modest amount more. I also want to note as an aside that there are dual echo methods that just collect two echoes. So that would be like the red and the green echo. And that's essentially TR free because you can see that that's collected almost in the same amount of time. And those methods are helpful. I've highlighted 2 references in the top right corner if you want to look into them more often, in more depth. Finally, we can do that same 3 echoes, but with a faster readout time. So in this case, those 3 readout windows are each shorter, and the 3 echo times are each shorter. And what you can see if you look at the TRs on the right side, that there is a small increase in TR, but it's actually quite small. But what do I mean by faster readout? Faster readout could mean increasing your in-slice acceleration, which is like grappa and Siemens or acid and GE. It could be using larger voxels for the same field of view. It could also be just plain reducing the number of slices or using multi-slice or multi-band acceleration. In this specific example, I modeled this after the top 2 ones are the equivalent of using in-slice acceleration equals 2, and the bottom one is in-slice acceleration equals 3. So this is the actual equivalent of what they would look like if everything is identical except changing that one parameter. And this gets to the main point I'm trying to bring home, which is if you're looking at what your study goals, you should optimize your acquisition parameters based on those goals. And if multi-echo fMRI will benefit your goals, then you're going to optimize your other parameters accordingly to get it. And it's not a huge difference. To give a little bit more data to drive this point home, in this figure showing what the TR is if you're doing 1, 3, or 4 echoes. So if you look at the left side of this plot, if there's everything I'm showing now is just no multi-slice acceleration, so multi-slice acceleration 1. And if you have the very left, that's no in-slice acceleration. So to get essentially whole brain coverage with this data set, then 1 echo is going to be about a 2.5 second TR, 3 echoes is a 5.5 second TR, and 7 echoes is a 4 second TR. But if we increase in-slice acceleration, you see that we can get this volume in less and less time, to the point where if it's in-slice acceleration of 4, there's actually no difference in TR between 1 and 3 echoes. I can fill this curve in adding multi-slice acceleration options. And what you can see is as you're collecting more slices simultaneously, all the TRs go down, and the differences between 1, 3, and 4 echoes also goes down. They actually scale fairly proportionally. So if you're changing absolutely no parameter at all, and you are using in-slice acceleration of 2, then your TR is going to be about 40 to 50% more. If you're using in-slice acceleration 3, it's either a 14% TR cost. Sometimes I'll take that by reducing a few slices. And if you're in-slice acceleration of 4, you're actually getting a shorter TR by about 1%. That's if you're doing everything identically. But the other option is you can change your parameters. So if there's a small yellow line added in the middle, and you can see if you have multi-slice acceleration equals 2, but you're going from in-slice from 2 to 3, your TR is effectively the same. And again, if you're starting from that same point of in-slice and multi-slice acceleration of 2, and you just increase multi-slice acceleration to 3, your TR stays effectively the same. And just to give an idea of what the short TR looks like, my colleague Emily Finn has been collecting data, multi-echo, 3-echo data with a 1-second TR on our scanner, and these are the volumes. So you actually can collect these data. So now I'm going to talk about how multi-echo fMRI can help in general. There's 2 main methods I'm focusing on in this talk. The first is what's called the optimal combination of the echoes, which is a term I'm not in love with, but it's the term that's often used. It's essentially a weighted average. So you're taking essentially the weighted average of the however many 3 or more echoes you can, and they're weighted based on the VoxOI's T2 star estimates. These methods are old. I mean, the concept was 1999, the specific formulas are 2006, and the math is really straightforward. The big thing that changed, which might make more people consider this now than they did back in 2006, is scanner hardware is caught up. So now there's, and scanner pulse sequences have caught up. So now there's quite a few options to actually collect these data. And the math is not only simple, but it's automatically calculated in AFNI, fMRI Prep, and Tedana. And any other package that wants to add this, it's actually not that hard to add. The other method I'm talking about is denoising methods, which is a category I'd call of removing this 9 T2 star weighted signal based on models across echoes. So the 2 initial publications from this were in 2012 and 2013. And all these methods use empirical models of noise to get away from assumptions of what looks like noise. So what do I mean by that? There's one example of this, Jennifer Evans published a few years ago, where if you have a very slow neural change, normally we have to just regress that out because it's slow drift of fMRI. But because that slow neural drift might have T2 star weighting and the scanner drift doesn't, you can actually potentially separate those 2 signals. So that's an example of what these empirical methods could do. I will also note that as part of the Tedana project, which is going to be talked about more in the next talk by Elizabeth, we've added a lot of literature on all these methods, how they're done, other resources, other publications. So if you want to go beyond this, very brief explanation, please visit those links. The one study I'm focusing on showing you what these benefits can look like in reality is focusing on contrast to noise. So we collected this data set with 2 volunteers, each had 9 sessions, and across 9 sessions, 9 hours of data, we collected about 103 runs of 5-minute block design checkerboard. And the idea of this is, for that block design checkerboard task, we get a hemodynamic response. I'm focusing on 2 RIs, this lateral geniculate nucleus, which has a very small response, but reliable, and the calcarein sulcus, which has a fairly large response. So across these 103 runs, I have the hemodynamic response to the block design. The red line in this case is the median response for the 100 runs. The gray is the 75th percentile across all 100 runs. And the black outlines are the maximum and minimum. So what you can see is this is the middle of our 3 echoes, which is the equivalent of if you collected single echo fMRI. If you did optimally combined, so you're doing that weighted average of 3 echoes, what you can see is that gray area, the shape is the same, but that gray area, which is how much variation you see across runs, gets narrower. And even the maximum and minimum values get narrower. And they look visually similar after denoising. And we have the same general idea for the second volunteer, where the range of variation across these 103 runs decreases with time. So this is sort of qualitative visualization, but we can put some numbers to this. For every single run, I'm going to calculate a contrast to noise value. So the magnitude in our contrasted noise is going to be the difference between the peak value and the minimum value for each run's HRF. And the noise is going to be the residual, the standard deviation of the residual that didn't fit this model. So what you can see here is every dot is a single run. And for every run, there's a blue dot for the contrast to noise in the Calquin-Sulcus region of interest, and a red dot for the contrast to noise in the LGN region of interest. The two plots I'm showing from the two volunteers, the x-axis is the contrast to noise for the middle echo or the single echo comparison, and the y-axis is the optimally combined contrast to noise. The solid diagonal line is unity. So that means that if the contrast to noise doesn't change, it's going to fall along that line. What you can see is every single dot is either on or above that line, which means in every single run, doing the optimal combination of echoes is giving us increased contrast to noise in both the Calquin-Sulcus and the LGN. Now, if we look at echo 2 versus denoise, you can see that in almost every single run, we're also again seeing that contrast to noise increase. It's a little bit more variable run to run, but sometimes those increases are quite large. Now, if I compare optimally combined to denoise, you can see denoise does increase contrast to noise in almost every single run, but it's not quite, it is variable a little bit. So another way of showing this is a distribution of all these runs. So in this case, I'm showing distributions from volunteer 1, the Calquin-Sulcus. If you focus first on the purplish line, what you could see is the improved contrast to noise from the middle echo to optimally combined is on average on median about 18%, and it varies from 8% to 30%. So that's, getting a 20% increase in contrast to noise is nothing to ignore. If you look at the increase in contrast to noise from denoising versus middle echo, the yellow one, you can see that in this case, it's the median is over 25%. And sometimes, there's a few runs where it's almost 50% increased in contrast to noise. Now, if you look at denoise versus optimally combined, you'll notice that the median is about 8%, and most runs we are seeing an increase, but there are a few runs where it does get worse. So that is volunteer 1 Calquin-Sulcus. We can also look at volunteer 1 LGN and volunteer 2 for the same regions of interest. And what you can see in all 4 of these, the numbers vary a little bit, but the pattern is the same. So we're getting a substantial increase in contrast to noise for optimally combined. We're getting on average an increase for an additional increase for denoising, but it does vary a little bit across runs. So if you're looking at this open eyes, I could say optimal combination reliably improves contrast to noise over single echo. If you're not changing any other parameter and you can get those 3 echoes, there is no, it's going to give you a benefit. Denoising can be similar, much better, or a little bit worse than optimal combination. So I would say the denoising methods are a work in progress. We've made a lot of effort on that. You'll hear a bit more of that in Elizabeth's talk next. But there is more to understand and improve on how these methods are empirically defining the noise to remove. Even then, I would say it's fine to use denoising, but this is something you want to check your results for. If you're optimal combined, I think you're pretty safe saying you know what it does. For denoising, make sure nothing surprising happens. I will also note that one issue with denoising in this data set is there are limits that present the data. The first limit is a limit I wish we all have, which is I had awesome volunteers. So these volunteers, there were, across the two of them, there was 206 5-minute runs. In all but 2 of them, they moved their heads less than 1.5 millimeters. And the last 2, I think they were less than, I think one was 2.5 millimeters. One was right around 1.5. So they didn't move. The scanner this was scanned on was a single scanner. It was extremely stable. There was regular quality assurance testing. So everything that could add noise to this data that we had control over was really, really stable. And there's evidence from other papers that the benefits of denoising will be greater if there was more noise to remove of either head motion or scanner instabilities. So it's possible that if you have a messier data set, you might actually see a bigger improvement. As a final summary and recommendations, I would say you can acquire multi-echo data. It's balanced with a combination of maybe slightly increased accelerations or decreased slices and an increased TR. The increased contrast to noise from optimal combination should balance lower SNR and acceleration. With this point, I will also note that, I'm not actually showing data that it does balance, but based on what I'm showing, I think it should. But this is something that could easily be tested in scanner piloting. So I don't know how much time Angela Laird in one of the following talks will have to go into this, but they did active piloting to show that their data quality was not affected or improved by multi-echo based on whatever parameters they change. So if you're curious about that, use your, as you're optimizing parameters, you should test it. It is very testable. With multi-echo data, you can empirically identify and remove this non-T2 weighted sound, but I will say these algorithms are under development and should not be blindly used. And I am very confident in saying these methods will get better. Visit the Tedana Project's website and listen to Elizabeth's talk next. As far as general recommendations, I think at this point, if you're thinking today about starting a study and you're assuming we can collect data, and you're planning to go from acquisition to publication in a couple of years, and you're not going to really look at that data afterwards, I think it's worth considering multi-echo. You might see modest benefits from optimal combination. If you're planning a longer-term project with goals of longer-term data reuse, I would strongly consider multi-echo. Like I've said, there are immediate modest benefits from just doing optimal combination. And I think as these denoising methods get more robust, more reliable, and more stable, it's very likely we're going to see larger long-term benefits. And in addition, I focused on just these two methods, but there are completely different ways we can use multi-echo fMRI. For example, see Cesar's talk also in this series to get a sense of a completely different way we can use multi-echo fMRI to understand data. Speaking of which, the other 4 talks in this session, Stefano talked before me, and Elizabeth, Cesar, and Angela are coming afterwards. So please watch all of them. And finally, I'd like to acknowledge the people that were involved in the 100-run study and the Tedana community, involving many people. And maybe if you're interested in this talk, that can include you as well. Thank you very much for your time.
Hi, everyone. Today, I'm going to be talking about Tedana software and community as part of the Multi-Echo fMRI Methods and Applications Symposium. And first, I want to explain a little bit why I'm talking about software in particular. This is something I know many of us as researchers aren't used to focusing on, but I really want to make the argument that methods depend on software. And to explain a little bit what I mean, I want to point out first that when we're thinking about research methods, and how they can be used to answer different experimental questions, it's important to recognize that different methods need to be benchmarked against a wide variety of data sets. Because what can end up happening is a method that works really well to answer one experimental question, if we change the data set even slightly, the method may not perform in the way that we expect. And it's hard to know ahead of time the dimensions along which we can change data sets that will impact performance. The other thing to point out is that experimental methods have become really tightly linked with analytic software choices. And what I mean by that is that when we think about applying a particular experimental method, different implementations of that method with the same software or running that software on different operating systems, for example, can actually lead to different results. And so therefore, the software has become a really defining feature of what is a method today. And so if we combine these two together, when we're thinking about how we want to apply methods to a broad variety of data sets, and we need methods that are linked with software choices, what this means is that we end up needing software that can be easily applied to a wide variety of data sets and easily understood by many different researchers. And so therefore, the code needs to be understandable and usable in order to best achieve this goal. So putting this in context, we were really thinking about how we can use this kind of framework or this kind of approach to think about how we process multi-echo data. And in particular, we were really interested in something called MICA. So MICA, or multi-echo ICA, is a multi-echo denoising method originally introduced by Kundu and colleagues in 2012. And if you've heard Dan or Stefano so far in this symposium, you may know a little bit about it already, but just to kind of recap what the main steps are, the idea is that you collect at least 3 echoes, and you use these to create a T2 star map that represents where signal is coming from for each voxel for each of the echoes. And then this T2 star map can be used to create a weighted time series, a weighted average time series. In the multi-echo literature, this is often called the optimal combination. And then perhaps what's somewhat unique to multi-echo ICA is that we then perform a decomposition of the resulting time series using PCA and ICA. And the resulting components can be classified as signal or noise based on an internal decision tree. So we have this general approach, this general algorithm, and we had a reference implementation. So shortly after MICA was first published in 2012, a reference implementation was distributed in AFNI, the large neuroimaging software package. And this may be familiar to many of you as mica.py. And because this reference implementation was available, this allowed the method to be tested on a wide variety of data sets, which, as I mentioned before, is crucially important to be able to ensure that the method works as intended. However, because of the distribution model, method development remained largely of the responsibility of Prantik Kundu, the first author, as the sole package maintainer. So what this often meant in practice is that as different research groups used the method, and they went to then feed back the improvements that they had learned or gathered based on their own experience working with the data. Unfortunately, it became a situation where the maintainer was a bottleneck to the method. And this is very, very common in that it's really hard to create a structure where you can feed back improvements. And so one of the things that I was really interested in at the time was how could we think about a different structure where we could actually have a way to feedback improvements more regularly as more people use the method on different data sets and in different environments. And to do this, I was really inspired by a lot of the work on different academic software projects that focus on community-driven methods. And so we wanted to figure out how could we bring this framework to mica.py. And so to do this, we created TDANA, or TE Dependent Analysis. So this was originally created to improve and extend MICA, and this is was originally introduced in 2017. The goal then was to preserve the overall functionality of MICA, so all of those 3 steps I pointed out to you previously, but done in a modular, tested, and pure Python implementation. And we hoped that this updated implementation would help convert MICA into a community-driven method. So because we now were focusing on making the code usable, extensible, and understandable by a wide variety of researchers who could deploy it in their own data sets, we hoped that it would remove the bottleneck where that's so common in so many academic software projects, so that improvements could be pushed directly to the software and therefore directly to the method itself. So to do this, we've really focused on a core approach, which is that we provide documentation and readable code to make multi-echo methods more accessible to both users and developers. And what this means is that we're providing really general information on multi-echo across the entire acquisition and processing lifecycle. So as you can see here, this is just the sidebar from our documentation website. We have sections that are specific to TDANA, such as using TDANA, the TDANA pipeline, and outputs of TDANA, but we also have more general sections, such as what is multi-echo fMRI, how can you go about acquiring multi-echo fMRI data, what are some resources to get you started. And again, we really wanted to focus on implementing the original functionality of MICA, as well as relevant extensions that have been proposed over time. For example, we now support multiple T2 star curve fitting methods. So there are multiple methods by which you can generate T2 star maps. And if you're interested in learning more about the particular details of what TDANA currently can and cannot support, I'd really encourage you to check out the Read the Docs website that we've set up, in particular the TDANA pipeline section. So, you know, I said we wanted this to be a community-driven software. We wanted people to be able to feed back their improvements directly to the method. And I'm really happy to say that we have grown quite a community recently. So since 2017, we have moved from just 1 or 2 contributors to over 17. And these are from over 10 institutions with a really strong core developer team. We have monthly open developer calls. We have a semi-regular newsletter which I'd love to see both of you or both of those more widely known. So you're welcome to come to any of those or subscribe to the newsletter. And so far, we've had one dedicated hackathon that Dan Handwerker organized at the NIH. So despite all of these successes, we do have some challenges that I think are really important to point out when thinking about this kind of framework for software in science. So the first is that the conversion rate of users to contributors is low for any scientific software. So what I mean by that is that as you make a method available, people will use that method, but the number of people who will have something they're interested in feeding back or something they're interested in changing will be low. And as we're relatively domain specific, we're not only fMRI, we're multi-echo fMRI and one particular approach therein. Currently, this has translated to a small absolute number of developers, which means that, for any given developer, it's still a decent amount of work. We do not yet have an academic publication describing the software, so this is largely by choice, but in the current academic cycle or incentive structure, where you need to publish semi-regularly, this is obviously not the norm and can present challenges for individual researchers. Also, because we're operating outside of traditional grant-based or institutional infrastructure, developing governance structures remains an ongoing conversation. So what I mean by that is you can't just turn to whoever is the named PI on the grant. We're all on equal footing, which presents new challenges and I think really exciting opportunities. But so if we consider this set of challenges and we kind of take a step back, we can see that it actually mirrors broader challenges that have been described between academia and community-driven open source. So this is a table that Fernando Perez made for his presentation at the National Science Foundation last year. And here you can see that along dimensions, including credit, collaborators, authorship, peer review, you can see that the incentives in open source and in academia are still not quite aligned. So this is a really general challenge that most software-focused endeavors are facing right now. So all that being said, I do think it's important then to acknowledge that these challenges have led to some trade-offs. The first is that consciously building a community takes time. So starting from 1 or 2 and getting to 17, it doesn't happen overnight. And that time is not accounted for in traditional funding cycles. Additionally, it's always easier to get funding for creating a new method than for maintaining the software that supports an existing method. Although I do think this is changing, I think this is still by and large true, particularly at the established funding agencies. That being said, with this trade-off, I think there's a certain amount of potential that's really promising. The first is that we can only do what makes sense in a given moment. So obviously these things take time, but any steps you can make in this direction, I think are really promising. And I do think that moving in this direction can result in long-term gains, both for individual scientists and for the method itself. And what I mean by that is that as individual scientists, we're obviously interested in seeing methods that we propose or work with succeed, but it can also create a structure where you can have a really solid base of contributors and collaborators across many of your projects. All right, so if you're interested in moving to this kind of framework, how can you go from a new method to a community project? There are a couple of things we've learned that I think are really important. The first is that making code available online isn't enough. We really need to consciously think about how colleagues can interact with our code. And the very first step is just ensuring that it works across a variety of platforms. So this could be different operating systems, different versions of language. So for us, this is different versions of Python, but just making sure that the method is accessible is really important. And also consider adopting documentation-driven development methods. So we as scientists are really used to explaining our experimental protocols and the particular process we use there. But if we take this focus on explanation and we move it to documentation for software and for a particular method, it can be really impactful in making sure that it's used in the appropriate context and that it's accessible and understandable to the widest variety of researchers. So with that, I just want to point you to the other talks in the symposium, which I would highly encourage you to check out. I think they're all really wonderful and point to really exciting directions in multi-echo fMRI. I'd like to say thank you to my supervisor, Jean-Baptiste Pauline, my lab, the Origami Lab, and everyone who's contributed to Tadana so far. It's really been a wonderful group, and we've been so lucky to have them. And we'd love to have you involved if you're interested at all in multi-echo fMRI. And if you'd like to get involved, I just want to leave you with a few resources on how you can get started. And with that, thank you.
Hello, I'm Cesar Caballero-Gaudes from the Signal Processing in Neuroimaging Group at the BCBL in Spain, and the title of my talk is Multi-Echo Beyond Preprocessing as part of the Symposium, 2 is better than 1, and many are better, multi-echo fMRI methods and applications. When we want to perform a functional MRI experiment, typically we plan and design the experimental config interest and the paradigm in advance. Then we go to the MRI scanner, decide the parameters of the sequence, and collect one image at each repetition time or several images in case of multi-echo acquisition to get a time course per voxel. Check these other talks of this session if you want to get more information on how to decide if your study can benefit from a multi-echo acquisition or about key practical steps when planning your multi-echo fMRI experiment. After the data is collected, you perform data preprocessing, which in the case of multi-echo acquisition will probably include optimal combination of the different echo datasets, or even denoising with a multi-echo based approach like multi-echo ICA. And I would recommend that you check the talk about the Tadana software and community to learn about how to perform multi-echo fMRI analysis with Tadana and how to get involved in its development. Then, based on the timings of your experimental paradigm, you can formulate a model of both time courses in response to the different conditions and usually perform a general linear model analysis based on that hypothetical model to perform a statistical inference on the model and compute the nice activation maps that we all want to obtain to study brain function. In model-based analysis of fMRI data, we usually assume that the ball response to neuronal activity can be described as a linear model where the changes in the stimulus signal or activity-inducing signal are saved by the hemispheric response. This process is known as convolution. Then, this ball component is corrupted by noise in the acquired fMRI data. However, we don't know the timings of the stimulus or changes in the neuronal activity in advance, as in naturalistic paradigms, resting state, or clinical conditions. It is difficult to establish a model to perform the analysis in these datasets. One possibility is to deconvolve the fMRI data in order to estimate the activity-inducing signal generating the ball responses. This is done by solving an inverse problem assuming a forward hemodynamictomy. The convolution of the ball response is a key step to study functional connectivity at the neuronal level, and it's often used in analysis of psychophysiological interaction. Although there exist multiple algorithms for ball deconvolution that operate within one time course per voxel, there is none that is tailored for multi-echo fMRI data. And in this talk, I'm going to introduce an algorithm named multi-echo sparse paradigm-free mapping with these goals in mind. The formulation of this algorithm relies on the same model as previous deconvolution algorithms with one dataset, either collected at a single echo time or the optimally combined dataset, in that the activity-inducing signal is saved by the hemispheric response. Now, the difference is that according to the model of multi-echo fMRI data, the time course of signal percentage changes in one voxel at one echo time can be modeled as a ball component associated with relative changes in the transverse relaxation parameter, R2 star of the voxel, that shows a linear dependence with the echo time, and a component that depends on relative changes in the normalization of the voxel plus noise. In our case, it is reasonable to assume that the neural activity generates hemodynamic changes, in other words, a ball response, that have the same temporal pattern across all of the echo datasets, but each of them is scaled by its own echo time, and that the changes in the normalization will also be equal across the echoes, plus some noise component. Therefore, we can establish a deconvolution algorithm that is tailored for multi-echo fMRI data that it considers all of the echo dataset as an input, and aims to estimate maps of the time-varying changes in the activity-induced signal underlying the ball responses that are now defined in terms of relative changes in R2 star. More information about the mathematical details of the method can be found in our publication in NeuroImage. As a proof of concept, we have validated this algorithm in a multi-echo fMRI dataset acquired at 3 echo times at 3 Tesla, where subjects perform a random fast event-related paradigm, including 5 times. Regarding the data analysis, the 3 echo datasets were preprocessed with a standard pipeline implemented in ACRI that optionally included optimal combination of the echoes and multi-echo ICA as part of the preprocessing in order to evaluate the influence of these steps in posterior analysis. First, we analyze the data with a standard regression analysis, either at the task level, where the model includes one regressor for each of the 5 experimental tasks, or at the trial level, with one regressor for each of the trials of the paradigm. In other words, single trial analysis. This analysis employed the timing information of the paradigms and were performed on the optimally combined dataset after denoising with multi-echo ICA, because this dataset could be interpreted as the one that gets the best possible preprocessing considering a multi-echo fMRI acquisition. In addition, we analyzed this dataset with our previous sparse paradigm-free mapping algorithm that was proposed for single echo datasets. And finally, with the multi-echo sparse paradigm-free mapping algorithm using the 3 echo datasets as input, either with or without multi-echo ICA as part of the preprocessing. The 1 echo and multi-echo sparse paradigm-free mapping algorithms are not aware of the timing of the trials in the analysis. Importantly, the SPM canonical HRF was employed in all the analysis. An important observation is that the output of multi-echo sparse paradigm-free mapping is not a single activation map, but another dataset with the estimates of R2 star changes and optionally changes in the net magnetization for each TR. These results are better explored as a movie. On the top left, we can see the sequence of paradigm events, which should be representative of the times of neuronal activations. On the right, you can see the same movie, but temporally smoothed by the hemodynamic responses, by the hemodynamic response as a reference for both signal changes. And on the top right, you can see the histograms of the estimated changes in the transverse realization parameter at each TR. In the middle figure, you can see the maps of the estimates of changes in R2 stat that are estimated with multi-echo sparse paradigm-free mapping. And at the bottom, you can see these changes saved by the hemodynamic response. In the movie, you can see that the estimated maps show negative changes in R2 star in areas of the auditory and visual cortices at the time of the trials when the subjects were listening to music and had to indicate which instrument was being played, or negative changes in R2 star within the fusiform gyrus during the viewing of houses or regions of the lateral occipital cortex during trials with dot patterns resembling biological motion. We can also observe activations in regions in the reading network, such as lateral parietal or inferior frontal gyrus in the left hemisphere in trials for reading sentences, or the presentar circles and supplementary motor area for the finger tapping trials. All of these events were detected without knowing their timings in advance. And I will encourage you to stop the movie and check the map and go to this website where all the videos for all the subjects are available. Here, in this figure, we can see the activation maps for a single trial of a particular subject corresponding to watching images of houses for the 4 types of analysis. We can see that the activation maps obtained by multi-echo sparse paradigm-free mapping have much larger spatial overlap with the single trial activation map that is obtained when we know the timing of the trial. The maps show negative changes in R2 star in regions of the fusiform gyrus and occipital cortex, as expected. In addition, we can also see some positive changes in R2 star in areas of the medial superior frontal gyrus that also appear in the single trial GLM maps. Clearly, the maps obtained with multi-echo sparse paradigm-free mapping offer larger sensitivity than the one obtained with its single echo counterpart, demonstrating the advantage of the multi-echo formulation. In addition, we can see that applying multi-echo ICA helps to improve the performance of the composition, reducing the detection of potential artifact-related events due to motion or inflow effects. Using the task level GLM activation maps as a reference, we can also evaluate the benchmark. We can also evaluate and benchmark the sensitivity and specificity of the different approaches. When the trial GLM activation maps are thresholded at a force discovery rate of 0.05, we can see that these single trial level maps offer a very high specificity but low sensitivity, which is almost equivalent to an uncorrected threshold of p-value 0.0001. When we decrease the threshold, of course, we clearly see an increase in sensitivity with a little decrease in specificity for some trials. In contrast, the one-echo sparse paradigm-free mapping algorithm offers a high specificity but very, very low sensitivity. This is the penalty of being blind to the timing when detecting the events. However, with the multi-echo formulation, we can recover a high sensitivity at the cost of reducing the specificity of the detected events. And using multi-echo ICA in combination with multi-echo sparse paradigm-free mapping helps to improve a little bit the sensitivity and specificity of the detected single trial events compared to the task level maps. This performance in terms of sensitivity and specificity can be observed across all the different experimental tasks of the paradigm, and it's also observed when the single trial maps are compared with its GLM equivalent, which is a fairer comparison because all the maps are compared at the single trial level. An important benefit of the convolution approaches is that we can study events that occur unrelated to the paradigm in an exploratory manner, because the analysis is not constrained in terms of timings. For example, here we can see the activation maps in terms of changes in arthro-stat at several times during resting periods of the paradigm. These maps of spontaneous changes in arthro-stat clearly depict activations in areas of the default mode network and the dorsal attention network, which show opposite polarity in the amplitude of arthro-stat changes. These maps could not be obtained with a standard GLM approach since we don't know when they occur. We can see that all the regions belonging to the same network don't show the same polarity in the activation. For instance, the map at time 316 seconds shows that the left and right regions of the dorsolateral prefrontal cortex that are part of the dorsal attention network have different polarity. These maps demonstrate that multi-echo sparse paradigm-free mapping also allows studying dynamic changes in activations within functional and between functional networks in a data-driven and exploratory manner. In other words, we can study dynamic functional connectivity. In addition, the process of the convolution can be understood as a denoising or filtering approach where the filter is matched to the shape of the fMRI response. But what kind of signal are we recovering? This figure shows the voxel-wise correlation of the time course fitted to the trial level model. In other words, the signal changes generated by all the trials according to the timing of the paradigm, with the time course deconvolved by the one-echo sparse paradigm-free mapping algorithm and the multi-echo sparse paradigm-free mapping algorithm. Clearly, the multi-echo SPFM approach offers much higher correlation with the model-based fitted signal than the one-echo algorithm, whereas the one-echo SPFM approach only has high correlation in boxes of the primary sensory cortices related to the task. The multi-echo SPFM deconvolution obtains a much larger correlation not only in these task-related regions, but also in most of the cortical gray matter, and also in subcortical regions, and also the cerebellum. This increase in the correlation is due to the increase in sensitivity, but a correct level of specificity since the correlation is still very low in white matter boxes. Instead, if the correlation is done with the optimally combined signal and multi-echo ICA denoise dataset, we can see that the multi-echo SPFM results have a very high correlation with this dataset in the whole cortex, the cerebellum, and the subcortical areas, such as the putamen and the caudate nucleus. The difference in correlation between the top figure and the bottom figure can be probably explained because the multi-echo SPFM algorithm is able to discover more bold events during resting periods that cannot be captured with a model-based approach and are not detected with the one-echo SPFM algorithm due to its lower sensitivity. So to summarize, we can say that not only does multi-echo fMRI increases the contrast to noise ratio and help denoising of the fMRI signal, but it also improves the deconvolution of the bold responses. Multi-echo sparse paradigm-free mapping, the algorithm that we have presented, reliably detects individual events. In other words, single trial responses at the single subject level without prior information of their timing, some kind of blind detection. The multi-echo SPFM activation maps offer larger overlap with those obtained with model-based GLM analysis than its single echo counterpart. And the combination with multi-echo-based ICA denoising further improves the quality of the results. In addition, an advantage of multi-echo SPFM is that it yields time series of estimates in time varying changes in R2 star. So it has interpretable units. Therefore, I think that multi-echo SPFM can help us to decipher the dynamics of brain activity in naturalistic paradigms, predestined or clinical conditions with unknown event timing in a pseudo-quantitative manner. For your information, the multi-echo sparse paradigm free mapping algorithm is already distributed within AFNI. I will encourage you to try it on your multi-echo fMRI data, and don't hesitate to contact me by email or in the AFNI message board if you want to give any comment or need any support. And finally, I want to thank the members of our group in the signal processing and emerging group at the BCBN and collaborators at the National Institute of Wales of the Functional Imaging Methods and the AFNI group and our funding sources. And finally, don't forget watching the other 4 talks of the sponsor. Thank you very much.
Thanks to Stefano and Dan for asking me to contribute to this symposium. I'm a relative newcomer to multi-echo MRI, so the focus of this presentation is to provide a real-world illustration of how a typical cognitive neuroscience lab might go about adding multi-echo fMRI to their ongoing research. My lab is located at Florida International University, which is an urban public university in Miami, Florida. I'm also the director of the FIU Center for Imaging Science, which hosts a Siemens Prisma. We're an ABCD site, and other work at the CIS focuses on children and teens, as well as on adult substance use and HIV. My lab became interested in multi-echo fMRI a year or so ago for all the reasons that have been discussed by the other presenters in this symposium, including increased temporal signal-to-noise ratio, enhanced ability to remove motion and other artifacts, and to boost statistical power. We also became interested given the strong and welcoming open source community that is developing Tadana. But as our other studies were already leveraging multi-band EPI sequences, we additionally wanted to pursue multi-band multi-echo fMRI, which offers the same benefits as multi-echo MRI with a reduced cost and temporal resolution, as well as the ability to easily acquire complex magnitude plus phase data. And before proceeding, I want to give a big shout out to 2 graduate students in my lab, Taylor Solo and Katie Bottenhorn, who are responsible for driving this work and basically taking me along for the ride. Their enthusiasm for this new frontier was very contagious, and it's been exciting to work with them. So with that background to give you the context, let's talk about how we got started on this journey. As researchers, we know that new things are hard and that we're all used to encountering obstacles. But multi-echo MRI has been around for a while now, but has not been adopted on a large scale. So we thought it would be helpful to walk you through our experiences and show you our path forward in the hopes of possibly letting our experiences inform others. The first thing you'll need is a multi-echo pulse sequence. At FIU, we use the multi-band multi-echo EPI sequence distributed by the awesome folks at the CMRR at the University of Minnesota as part of their multi-band EPI package. Special thanks to the developers of this package, it's been essential to our success. To acquire this sequence, you will need a master research agreement, which likely your institution already has, plus a C2P agreement between you, CMRR, and your vendor. And note that this slide is mostly Siemens specific, but the process is the same regardless of your vendor. The first step in the C2P process is to contact your imaging center director so that they can be looped in and assist as needed. Then you'll need to contact your regional representative for your scanner vendor. The rep will ask you for details about the sequence and its distributors and will prepare a contract. And then that contract will need to be routed through your research office's branch that handles contracts and agreements, and likely will need to be sent through multiple departments, including but not limited to legal, privacy, technology and intellectual property, and research integrity. And once it's been cleared by all the necessary departments, you and the individual who provides official signatures on behalf of your institution will send the partially signed C2P agreement to Siemens, who will sign it. Then you can upload the fully executed agreement to the CMRR portal, after which you'll be provided with access information so that you can finally download the sequence. So while the process involves 3 main players, you, Siemens, and CMRR, there are really lots of people involved. So fair warning, this process can take quite a bit of time, And you need to be sure to factor in months, not weeks, for the C2P into your project timeline. But then the fun starts. Once a sequence is installed, our next stop was to determine the appropriate parameters for us and build our protocol. And to do this, we relied on several resources that are distributed via Tadana. Thanks to Logan Dowdle and the Tadana community for providing a Google Sheet of published multi-echo studies and their associated parameters. Tadana members, including Dan Handwerker, have also been very gracious in sharing their actual protocol specification files, which were extremely helpful. And there's a corresponding OSF repo to share these PDFs among other researchers. Now, there's no gold standard multi-echo fMRI protocol, so these resources were very important to us. We sought to build our protocol while balancing the number of echoes, the acceleration, the spatial resolution, and the temporal resolution. Note that this was not a fast process, and we needed lots of piloting at our imaging center to optimize and finalize our protocol. Thankfully, this work was considered a benefit to the center, so these hours were provided free of charge. And at the bottom, I've provided our final set of parameters for you to review. One area where we encountered a few additional hurdles was how to consider the inclusion of physiological recordings. Thanks to Katie for her work on this. Physiological data, including electrocardiogram and electrodermal activity recordings, can add valuable information about a participant's physical state to a study, quantifying stress, arousal, and cardiac events. However, most of the research on simultaneous fMRI physio recordings has been done with single echo, single band, bold sequences, and these introduce minimal MR-related noise to the recordings. Multi-band, multi-echo sequences introduce additional noise due to RF and gradient pulses that allow us to collect multiple volumes per TR and multiple slices simultaneously. So here we have 15 seconds of an ECG recording collected in the scanner bore, but in the absence of a pulse sequence, using BioPAC's MR amplifiers, which are able to filter out some, but not all, of the MR-related noise. And below that, we have 40 seconds of ECG data collected during our multi-band, multi-echo sequence. Power spectra highlight the sequence-related noise in frequency bands corresponding to slice collection, shown by the green arrows, and TR, shown by the pink arrows, and their harmonics. And the first step in ECG data cleaning, regardless of the MR environment, is to filter out respiration with a 1 Hz high-pass filter. And to deal with the sequence-related artifacts, we apply a cone band stop filter implemented here as a series of IIR notch filters centered at 10.33 Hz for the slice collection and 0.66 Hz for TR and the harmonics up to the Nyquist frequency at 1000 Hz. This results in a cleaned ECG signal as shown at the bottom with clear R peaks and a power spectrum that more closely resembles that of the ECG data collected in the absence of the MB-ME sequence. Moving on to electrodermal activity, or EDA, prior research has shown that EDA recordings are not corrupted by sequence-related artifacts. But here's an example of EDA data collected in the MR environment in the absence of a pulse sequence. Below that, we have EDA data collected across a scanning session during multi-band, multi-echo scans. After a 15 Hz low-pass filter, which is the usual first step in EDA processing, it becomes evident that there are sequence-related artifacts in the same frequency band as seen in the ECG recording shown by the green and pink arrows, although to a much lesser extent. By applying the same series of notch filters to EDA data, we are able to remove sequence-related artifacts as shown at the bottom. So we learned a few additional lessons along the way. Once we started collecting data, we realized how much data we're actually generating. After all, we're acquiring 4 echoes, complex data, and have a 2-hour protocol. So our typical data set is 27 gigabytes per participant. We, like many other centers, use XNAP for our long-term image archive. And we quickly learned that pushing a large amount of data from the console to XNAP puts a lot of strain on our console. And sometimes it can hang up or even crash the system. As a result, we now only push data to XNAP in the evenings after participant scans have ended for the day. We learned to do this the hard way when we tried to push data before an ABCD scan and nearly missed the appointment. And as good citizens at our center, we definitely don't want to be causing problems for other studies. I think it's also important to know that the initiation and launch stages of the project were fairly uncharted waters for us. There are a lot of different models for imaging centers, and ours relies on professional MR technologists to run the console. Our team has learned it's important to have strong rapport with the text, to treat this as a collaboration and an adventure. And this really helped us make progress during the challenging times when we were building and optimizing our protocol. Finally, we want to acknowledge the excellent community of users and developers that we relied on. One of the reasons we were drawn into this work was because of the Tadana community. We, like a lot of other folks, have also found NeuroStars to be helpful. Thank you, INCF. Additional thanks to the CMRR multi-band GitHub repo and the Siemens Neuro user group. We were able to launch data collection for our study in February, and sadly, like so many other neuroimagers, our project was shut down in early March due to COVID-19. And like so many others, we're really looking forward to getting back to campus and resuming our study soon. We hope that our experiences may be informative to others, and we look forward to seeing lots of new multi-echo fMRI users in the future. Thanks very much for listening. And with that, I'd like to thank our team at FIU. I'm so grateful to get to work with this group. And again, special thanks to Katie and Taylor, as I would not be here without their hard work and determination. They're both graduating in 2021 and will be on the postdoc market soon. Finally, I'd like to thank NIH and NSF for their generous awards that fund our work. And for more information about multi-echo fMRI, please have a look at the other talks in the symposium presented by my colleagues Stefano, Dan, Cesar, and Elizabeth. Thanks again for listening.